So what is resonance? Let's go back to the tuning fork. If you remember the tuning fork, the sound that comes out of it is a sinusoidal pure tone wave. It's characterized by a certain frequency of vibration that's governed by the mass of the tuning fork and the stiffness of the tuning fork. And the tuning fork has its own natural frequency, or its frequency that it vibrates best at. So a sound is characterized by a certain amplitude of vibration. Depending on how hard you strike the tuning fork, that will determine the amplitude of that wave. The amplitude of vibration diminishes over time because of frictional resistance, and the decay in amplitude is called dampening, so eventually the vibration stops. If we were to take that tuning fork and touch the stem of it onto, say, a blackboard, what would happen to the blackboard? The blackboard would start vibrating, but it wouldn't vibrate at its own natural frequency. It's going to vibrate at the frequency of the applied force, or the tuning fork. We could touch the tuning fork to any metal surface, or any surface in general, but a metal surface would work best. And we can force that surface to vibrate at the natural frequency of the tuning fork. So when we hold a tuning fork against a hard surface, the sound immediately becomes louder. The sound has a greater power, a greater intensity, but it does not have a greater energy. The greater power that results from touching the vibrating fork on the hard surface is gained at the expense of vibration time. So if you remember, power is the amount of energy per second. An increase in power can be realized by either an increase in energy or a decrease in vibration time. So we take a tuning fork with its own mass and stiffness, we put it into vibration, it starts vibrating at its natural frequency. We hold that tuning fork up to a metal surface. All of a sudden the sound becomes louder, the sound is resonated. The hard surface is forced to vibrate at the frequency of the tuning fork. It's louder, but the vibrations end sooner than if the tuning fork were allowed to just go on its own. And that's the principle of resonance. When a periodic force is applied to an elastic system, the system is forced to vibrate at the frequency of the applied force and not the natural frequency of the system. The closer the frequency of the applied force to the natural frequency of the system, the greater the amplitude. So if I were to hold a metal tuning fork to a metal table, we get greater resonance than if I were to hold a metal tuning fork to a wood table, because the wood and the metal are different. The metal and the metal are closer. So for example, when a driving frequency is 100 Hz, the elastic system is forced to vibrate with a frequency of 100 Hz. When the driving frequency is 200 Hz, the elastic system is forced to vibrate with a frequency of 200 Hz. And this is known as force vibration.